kinetic energy of the gas. Then we said P is 2/3 of the kinetic energy over volume. Then we can bring in the ideal gas law. So we can say this is the first non-trivial result of the kinetic theory because it relates pressure, a macroscopic property, to the translational kinetic energy of the molecules. Translational means the one that the molecules are going in the x direction, y direction, or z direction, right? So then rewriting the above result for the pressure as PV is NmV squared over 3. We may combine it with the ideal gas law. So now we can bring in the ideal gas law into this. We can say PV is NKT. This is Boltzmann's constant. Okay? So here at this step, the other thing we can do is now say PV is NKT. And then what's going to happen here? I'm purposely not showing the whole page here on Wikipedia, just going step by step. So then it's going to be KB is Boltzmann's constant, T is the absolute temperature. So then what happens? Then, so you can now cancel the ends, right? And you get the relationship between temperature and velocity squared. And now we can bring in the kinetic energy again, right? We can say half mv squared average is the kinetic energy of each particle, whereas the kinetic energy total is the each particle times n, you see? And then, so whereas here, we're just doing the kinetic energy of each particle. So then you're gonna have what? Half mv squared, so let's see here. This 3 goes over to the top, is equal to what? mv squared average, right? Then divide by 2 here. And this is the kinetic energy of each particle. Now we finally give a microscopic meaning to temperature, the concept of temperature. So we're trying to kind of give microscopic meaning to pressure and temperature, because pressure and temperature are emergent phenomena. There's something that happens when we observe a big system and we say the system of gas has a certain pressure and a certain temperature. But what does temperature measure? What does pressure measure? Well, pressure measures kinetic energy of the gas, of the total gas, divided by its volume, right? And then what does temperature measure? Temperature measures the kinetic energy of each particle, but only each particle. You see, there's the N is missing. You see, so if I were to say the temperature of the gas, does it matter on how many particles there are? No, the big N is missing. It only matters on how fast a particular molecule is going in that gas, on the average. But it depends on the square of that velocity of that particular molecule. You see, and the N is missing. So we gave a microscopic meaning to temperature. You see. So it says the kinetic energy of the system is N times that of a molecule, namely K is half NV squared. Then the temperature takes the form T is equal to mv squared over 3 kb, which becomes, so 2/3 k over n kb. Equation 3 is one important result of the kinetic theory. The average molecular kinetic energy is proportional to the ideal gas law's absolute temperature. So I mean, they're kind of repeating the same things here. PV is 2/3 k, that's what this is. difference K. Thus, the product of pressure and volume per mole is proportional to the average translation of molecular kinetic energy. Equation 1 and equation 4 are called the classical results, which could also be derived from statistical mechanics. For more details, see 19. Since there are 3n degrees of freedom in a monatomic gas system with n particles, the kinetic energy per degree of freedom is okay. So one of the things that we also learned from this is, where did the 3 come from? See, so that it says the kinetic energy of each particle is 3. Remember where the 3 came from. When we derived the equation, PV is this one here, n over 3 mv squared. We use this fact that the v squared average is v initial x squared plus v initial y squared plus v initial y squared. And then we said these 3 are the same, and then this became like this, 3, and then v initial x squared became 1/3 of v squared. And then that's kind of where this 3 came from.
And the same is perfectly inelastic.
Yeah, and perfectly elastic. So if we lived if the universe was a 2-dimensional universe, what would have happened? If particles only could go in 2 dimensions, we would have only had this. Then this would have been 2. This would have been 2. So everywhere you see a 2, this would have been a 2. And then, of course, kinetic energy of each molecule, this would still be half mv squared, but then this would be a 2. You see? So everywhere we're seeing a 3, there it would be a 2. And then this would be a 2. So then what that means is that kinetic energy of a gas would be kT. And if it was a 1-dimensional, it would be half kT, right? So for 1D, for 1 dimension, the result would be half kT is equal to half mv squared. For 2 dimensions, it'd be 2/2 kT. And then for 3 dimensions, so this introduces the topics of degree of freedom. This is 1 degree of freedom, 2 degrees of freedom, and 3 degrees of freedom. So the conclusion is that for each degree of freedom, the kinetic energy of a gas is half kT. So if you live in a 3-dimensional universe, the kinetic energy is 3/2 kT. So if a gas is at 300 Kelvin, let's say, in a 1-dimensional universe, how fast are the molecules moving? V squared, so then the 2 and the 2 cancel, kT over m. Right? So the other way we could write this, by the way, half mv squared, I'm looking at this here, half mv squared average is equal to the 3/2 kT is the original form of the equation. Instead of writing let's see, 2 cancel, so for v squared, 3 kT over m. So the other way that a lot of times this is written is 3 RT over m, over molar mass. So this is the mass per particle, and then this is the mass per mole. So you can remember the relationship, number of particles is number of moles times NA, and then what was the relationship? It was Na times K is equal to R. So this relates the number of particles to the number of moles and Avogadro's constant. And then Avogadro's constant was, remember, 6.02. This is 1.38. So then the product of those is R. So if I want to change from KT over little n, because oftentimes I don't know the mass of a particle of a gas, but I know the mass of a mole of a gas. That's easier to use. So what I do here is I take the M, I bring it down into this, and then I change KT over M. I can use this. K is equal to R over NA, right? I substitute here, so look what happens. 3R, then the K becomes R over NA. And then what's this? Number of particles per mole, right? This is particles, that's Avogadro's constant, per mole. And then what is this? Grams per particle. In other words, how many grams is a particle of hydrogen, let's say, or particle of helium? It's grams per particle. So when you see an Na times little m, what is that? Look at what's the units of that. Particles per mole times grams per particle, particle cancel. You have grams per mole. That's called molar mass, which you can just look at the periodic table and you can determine the molar mass of a particle. So that's written with a big M, capital M. And the units of that is grams per mole. So we can write, anytime we see a KT over little m, we can change it to RT over big M. So V squared 3RT over big M. And then we can then square root that to find, this is called the root mean square of a gas. Square root of 3RT over M. So going back to that question, we could make a little short example out of this. Let's say we have H2O, gas, water vapor gas. Well, water vapor gas is likely to occur at anything above 100 Celsius, right? Because that's when water boils. So it's got to be at least 373 for water to boil. So we could say, let's say the temperature is 400 Kelvin. So if a gas is at 400, so if a water vapor, if a steam, let's say, is at 400 Kelvin in one-dimensional universe, what would the root mean square velocity be? So it'd be square root of what? Well, if it was a one-dimensional, the 3 here would change to a, let's see here. Oh, the 3 here would change to a 1/2, and then you'll have, you see, this will disappear, and then the 2 and the 2 will cancel. So the V root mean square will just be a KT over M, or the other way to write it would be RT over molar mass. So R would be 8.314. Temperature would be 400. What's the molar mass of H2O? Hydrogen weighs 1 gram per mole, right? And then oxygen weighs 16 grams. So in case if any of you have never had chemistry, because this is beginning to now sound very chemistry oriented, so let's assume you've never had chemistry. So introduce you to the periodic table and numbers on the top is the number of protons an element has, right?
The mass of the.
But I'm looking for something that also has the mass. These are the protons. Usually, the further down you get, the further to the right you get. Like when you get here, elements will usually have more neutrons than protons to keep the nucleus stable. So if something has, let's say, 79 protons, it's probably bound to have more than 79 neutrons, maybe 90 to 100. So I'm estimating that the weight of this will be 80 plus whatever neutrons it has. So if it has 100 neutrons, its weight is going to be 180, you know. When you go to the lower ones, the number of protons is more similar to the number of neutrons. So let's say lithium, 3 protons, it's likely to have maybe 3-4 neutrons. So it's probably going to, weight is supposed to be like 7, let's say. So, of course, remember the mass of the electron is negligible compared to the mass of the proton and the neutron. So we don't care how many electrons it has for its weight. Something that has, does this have the weight? Looks like that one does. So if you go to lithium, you see how it has 3 protons? Its weight is 6.94 grams per mole, which means almost 7. So that means it has 4 neutrons. You see that? So it has 3 protons, 4 neutrons. So slightly more than the number of protons, but not that much more. As you get heavier, let's say 24 protons, 52. So you subtract 52 minus 24, you get the 28 neutrons. You know why? Because the protons are repelling each other. So many protons in a tight space in the nucleus, they don't like each other. You need neutrons to help bind them together with the strong nuclear force. Otherwise, the protons would just repel and the nucleus wouldn't even exist. You see? So for H2O, then, of course, hydrogen, the weight is 1 proton. It has no neutron. So its weight is 1 gram. No neutron at all. Then oxygen is 8 protons, exactly 8 neutrons. Right? So its weight is 16 grams. The equal number of proton, and it looks like carbon, nitrogen, and oxygen have all equal protons and neutrons. 6, 6, 7, 7, 8, 8. But fluorine is 9, 19, so 10 neutrons. So carbon, nitrogen, oxygen have all equal protons and neutrons. That's kind of weird. I never thought of it that way.
And electrons.
And of course, electrons too. So the 3 most important things to life: oxygen to breathe, nitrogen, because 78% of the atmosphere is nitrogen. So that's our atmosphere. And then carbon-based life. They're all elements that have equal protons and neutrons. Okay. So then the H2O is going to be 16 times 2. No, sorry. H2 means 2 hydrogens, so 2 grams plus 16, that's 18. 18 grams per mole. Okay? But now change that to kilogram. Remember, this is molar mass, big M. So 18 kilograms per mole of the gas. That means if we lived in a one-dimensional universe, that's what the velocity average should be of the water molecule if it's at 400 Kelvin. So we put that into the calculator. 8.314 Kelvin divided by 0.418 square root. So on average, the molecules of the steam should be going at that speed, 429.8 meters per second. But if we live in a two-dimensional universe, so I'll try to make sense out of this formula. In a 2D, this is in 1D. In 2D, then what changes? Then of course, everywhere there's a 3, it becomes a 2. So let's see here. This becomes instead of a 1/2, it becomes a 2/2. So then the two cancels. This 2 goes up there. So then you have an extra 2. You see? So then you have an extra 2. So in a two-dimensional universe, so what's the answer? 429.83 times root 2. See? Because you have an extra root, you have an extra 2 in the radical. 607.87. In 2D. And then in 3D, okay, so in 3D, which is the universe we live in, you have a 3, 2, the 2 and the 2 cancel. Now, so we have an extra 3, right? Of course, that's the world we live in, the three-dimensional. So then you're going to do I'm going to divide by root 2 and multiply by, divide by root 2, multiply by root 3. 744. Okay, so now come to our answer. So the idea is this: if you have a steam whose temperature is 400 Kelvin, we know we live in a three-dimensional world, so that means on average the molecules are moving at 744.93 meters per second in random 3D direction, right? 744 meters per second. If I were to somehow squeeze this gas and allow only two-dimensional motion, or if we lived in a two-dimensional universe, they would only have to be going at 607 to yield the same temperature, right? And now if I were to squeeze them even more, they would only going in one direction. They would only have to go at 429 meters per second to yield the same temperature. So does that make sense? Why less dimensions, they don't have to go as fast?
There's motion.
Huh?
There's for like less energy used.
Less energy used?
The energy is not divided in 3 different ways. So X, Y, Z, X, Y.
Perhaps it goes back to how we derived everything, back to the box equation, and back to the motion, you know, from the pressure on one side of the wall, right? And we assume that in general, box goes in 3D. But even if you forget about that, you say, gas at 400 Kelvin in one dimension has to go slower than a gas at 3D has to go faster to yield the same temperature. It's not really sinking into my mind yet. If it's not sinking in, what can I do?
It would require more energy to change direction, so I assume it would have to go faster.
It would have to go, so you're saying in 3D, it requires more energy to change the direction of this? And that's why it's hotter? No, it's actually the same temperature.
Because the only energy it would produce is its speed.
If something is not making sense to me here, I might do something which might help. I'm not sure if it's gonna help, but it might help. I could now solve for the temperature in terms of the velocity, change the problem, right? So here I'm teaching you a technique. When you're stuck, never give up. So now take this equation and square this, and then 3RT over M, but now mv squared over 3r, and then solve for t in terms of the v. And now compare 3 boxes of steam, okay, one 3D, one 2D, and one, let's say 2D is like this, and then 1D is like this. And now make the velocity the same. So imagine V average here is 500 meters per second. The average here is 500 meters per second, but it's moving in 2 directions. Here it's moving only in 1. And then the average here is 500. You see what I did now? Now I made 3 boxes, each with the same velocity. What temperature will they yield? How hot will the gas be? Whereas here, I made the temperature the same, and I said, what velocity should they have to yield that temperature? Here, I'm saying they have the same velocity, what temperature will they yield? So in the 3D world, temperature is gonna be 0.018, 500 squared, over 3 times 8.314. You see? What's the top? 0.018. So that gas would be 180 Kelvin. Is that cold? 500 squared.
I think you divided by, or.
Huh? 3R. That gas was. Oh yeah, because if the gas was 400 Kelvin, it should have been going 744. So here, I made the steam go 500, right? So of course the temperature is gonna be colder than this temperature was what? 400 Kelvin. Okay, makes sense. Yeah, so that means steam, water vapor, whose root mean square velocity is 500, would give you a temperature of 180 Kelvin. So this gas will be 180 Kelvin. This gas, whose velocity is only in 2D, what's the temperature? So what changes? 3 to 2, right? Because remember the 2-dimensional was just the 2 here. So then what happens? The temperature should be warmer than 180. I can do it in my head. 540, 270, right?
Yeah, 270.
270. Ah, okay. So I think this way of comparing them, it makes more sense, at least to me. Because here, it's going velocity, but in 3 dimension. Its velocity is divided into 3 parts. So that same gas who is able to go in 3D, going at 500, will only be 180 Kelvin, whereas 2D gas will be 270. It's going to be hotter because its velocity is bound to 2 dimension only. It's going to be a hotter gas. You see? And then 1D, then you're just going to put 1, then it's going to be 540 Kelvin. That way of comparing them makes more sense. So this way the velocity is only in 1D, right? So now if you look at it from this point of view, right? If the temperature of this is hotter, the pressure is going to be more. You see that? Oh yeah, because the velocity is bound to 1 dimension. So when it comes and hits one side of the wall, it's going to come really fast because it's only 1D. But if it's 2D, it's coming like this. If it's going 500, part of the velocity is 500 this way, part of it is this way. So when it hits the wall, the force is not as much. So therefore the pressure is less here, and if the pressure is less, the temperature is less. And of course, if it's 3D, part of that velocity is X, Y, and Z. You see? So it doesn't hit the wall as hard, so therefore it's colder. If the pressure is less, it's colder. So now that it's making sense. The concept of those degrees of freedom, why it's 1/2, 2 halves, versus 3 halves. So of course the equation we're going to use most often is the one with the 3, because we're living in a 3. So you can kind of see now on the formula sheet where this comes from. See, 2/3. If we lived in a 2D, it would say 2/2. 1D would have said 2/1. And then if this was 1D, would have said 1/2. If it's 2D, 2 halves, and then 1D, 1/2, and then 3D, 3 halves. So this is 3 halves and then 1/2. So then, of course, if I'm trying to solve for V, the 2 and the 2 cancel, then I get square root of, and then this one comes down here, 3RT. So that gives you this equation. V root mean squared. See the bottom one here? One I'm trying to highlight. V root mean squared, square root of 3C, where C is what? Square root of RT over M, right? So square root of RT, that's this guy. And then you got square root of 3 times that. That's the root mean squared in a 3D. Now we need to talk about how do we get VP and V average. What do those mean? Well, in order to talk about that, you need to talk about the Stefan-Boltzmann distribution of gases. So that brings the whole concept of statistical mechanics into this. So now, so far we laid the relationship, we laid the groundwork for the relationship between temperature and velocity. So temperature, therefore, is the measure of the average kinetic energy of particles, right? And for each degree of freedom, you have half kT of energy. So the total kinetic energy in the 3D universe is 3/2 kT, okay? So therefore, we have a relationship between the velocity and the temperature. And we also have a relationship between pressure and temperature. So now let's get to the Stefan-Boltzmann. No, I think Yeah, no, I meant the Boltz, was it Maxwell? Yeah, Maxwell-Boltzmann distribution of gases. Okay, in physics, in particular statistical mechanics, because statistical mechanics is a branch of thermodynamics where it looks more at microscopic quantities, whereas thermodynamics looks at macroscopic quantities such as pressure, entropy, temperature, Gibbs free energy. Those are all thermodynamic quantities. The energy of a gas, the temperature of a gas, the pressure of a gas, Gibbs free energy of a gas, and there's all other stuff too. Those are macroscopic quantities. But at the microscopic level, what's happening? Particles are moving with a certain velocity. So when you have a bunch of particles, then you have emergent phenomena that happens, such as entropy, or entropy is a measure of disorder. So now let's quantify that and all of that stuff, right? Temperature is a measure of kinetic energy and so on, right? So statistical mechanics is that dwells on more the probability of the particles. What are they doing? So it says, is a particular probability distribution named after James Clerk Maxwell. So he's the same one that did the E&M, right? The electricity, the Maxwell's equations. And Ludwig Boltzmann. Boltzmann was the one who kind of founded the statistical mechanics. He had a bit of a nervous breakdown because nobody believed in his statistical mechanics theory, and I think he committed suicide because of that. I don't know why. But he probably had other stuff going on in his life which amounted to that, because it's kind of hard to believe that you would kill yourself just because no one's believing in you. Maybe, I don't know. It's like a weird story. So it says it was first defined and used for describing particle speeds in idealized gases, where the particles move freely inside a stationary container without interacting with one another, except for very brief collisions. So we're assuming that there's no forces between the particles, that they're randomly just moving, momentarily colliding with each other and the walls of the container. And they say exchange energy and momentum with each other or with their thermal environment. The term particle in this context refers to gaseous particles only, and the system of particles is assumed to have reached thermodynamic equilibrium. The energies of such particles follow what is known as Maxwell-Boltzmann statistics. And the statistical distribution of speeds is derived by equating particle energies with kinetic energy. Mathematically, the Maxwell-Boltzmann distribution is Chi distribution with 3 degrees of freedom. So in other words, they're saying Maxwell-Boltzmann distribution is a particular example of a wide variety of a distribution known as Chi distribution with 3 degrees of freedom. So what is Chi distribution? In probability theory and statistics, the Chi distribution is a continuous probability distribution. It is a distribution of the positive square root of the square of the sum of the squares of a set of independent random variables, each following a standard normal distribution or equivalent in the distribution of the Euclidean distance. It is thus related to the chi-squared distribution. Ooh, it's like, you gotta take statistics to really understand this. According, let's see here. I'm trying to get to as far as we need to get just to kind of get an idea of it. The most familiar examples of a chi distribution are Rayleigh distribution and the Maxwell-Boltzmann distribution of the molecular speeds in an ideal gas. So if we did like a little chart, we have chi distribution. Then we have it goes like this, it goes like this. This is Rayleigh distribution. And we have Maxwell-Boltzmann. This is 2 degrees of freedom. This is 3 degrees of freedom. So it says here, probability density function of the chi distribution is something of that form, where gamma of z is the gamma function. So that means that's the general chi distribution function. X of k x to the k minus 1 e to the negative x squared over 2 over, so basically you're like x to whatever power this is minus 1. So you could, I guess you could do, depending on the degrees of freedom, right? If this was 2 degrees of freedom, you would have here 2 minus 1, so it'll be x e to the minus x squared over 2. And for 3 degrees of freedom, it's x squared e to the minus x squared over 2. Yeah, that makes sense. And that's the Maxwell-Boltzmann distribution. It's a x squared e to the minus x squared. Right? Then you, on the bottom, you have 2 to the k over 2. Oh, that's also the degrees of freedom. 2 to the k over 2 minus 1. Gamma to the k over 2 squared. Where gamma is the k function. Cumulative distribution. The cumulative distribution function is given by the regularized gamma function. The moment generating function. Oh, the topics get very hard now. Oh, they bring entropy into the 2 here. Ln of gamma k over 2. Okay, related distributions. Chi squared function. If x is x of k, x squared is x of k, chi squared. Oh, chi squared is a particular form of the chi distribution. So I guess chi squared goes somewhere there. Then you have normal distribution. I think I've seen that one, normal distribution here. Well, that's called a normal distribution. So it's normal, probably we'll put it up here. Normal distribution. And they'll show you the graph of the distribution function. This looks like the one like for grades in the classroom. Let's say grades of a student in the classroom or something like we use just the normal distribution where it's f of x 1 over sigma standard is the standard deviation, square root of 2 pi. And then you got e to the minus some constant half x minus what? The mu is the average probably over the standard deviation. I think that's the average. over the sigma. So basically the normal distribution is like e to the minus x squared. It has similar behavior, but there's no x in the front, right? It's just an e to the minus x squared graph, and it goes like that. E to the minus x squared. So we could go to, like, say, a Desmos graphing calculator. Y equals, let's say, e to the power negative x squared. No, sorry, I should power. Okay, so this is the normal distribution they're saying. Just the regular y equals e to the minus x squared. Now if I want to shift it, let's say our first test next Monday, the test average is 80%, hopefully. Right? So it'll be x minus 80 squared. So how would we correct, if we want to follow the normal distribution, then we would do 2 times the standard deviation. So let's say standard deviation is 20. So 2 times 20, that'll be 40, right? Divided by 40. Right? And then
Is this
1 over sigma, huh?
Is this gonna be on the formula sheet?
No,
Oh.
because we don't need to do the normal distribution. This is for grade distribution or let's say age distribution or other kind of distributions. So 1 over what is it? Square root of 2 pi sigma. One divided by 20 is the standard deviation times 2 pi. How do you do pi here? Well, let's just put 3.14. What happened to the graph? Well, probably shifted, zoom out, zoom out. Oh, where's everybody? There's no students in that class? It flattened out? I was expecting it to go like this.
Maybe zoom out more. Oh, the scales are already up to 68.
Well, because I probably made it too flat, there probably should be a constant there for, when I integrate the function, it should give me the total number of students in the class, right? The area under the graph. Maybe I need something here, yeah. Did I write the normal distribution, right? Oh, you know what? This is done so that it's normalized to 1. So when you integrate it, you just get 1. So I think I could multiply this by, let's say there's 40, 50. Oh, okay, yeah. Let's say 100. Oh, you see that? So that means what? These are the totals what would that mean here? Let's see, this is the total number of students is 20. So that means how many students scored, how many students got an 80?
3, 2, 3.
Yeah, 3 students got an 80. Well, in order to know what that is, we would have to integrate this from 0 to 100. Probably that would be 0 to 100. And we would say the integral of this from 0 to 100 gives you the total number of students. And then depending on what the total number of students, we can put a certain factor on the top to say that factor is a fudge factor. So that the area under the curve is the total number of students. And you get a normal distribution function. You see? And then the Rayleigh distribution would be for 2D, you would put an x, and then here, this is the one that we deal with, the x squared. So you can kind of see that these distributions have quite a bit of a, let's see here. What other was there? So we have normal distribution, half normal distribution, so maybe on one side of the normal, Rayleigh and Maxwell, okay? There's another one that I found is called Nagakami distribution, Japanese. Has a weird kind of looking behavior. So a lot of times in physics, as you can kind of see with this, you come to a certain topic where you say, okay, is there a mathematical tool that we can use to enhance our understanding of what's going on? And then the mathematicians have already thought about this and revised it maybe for a couple hundred years. So when Boltzmann came along, this probably had been invented, or maybe he invented it partially, you know. So then Maxwell and Boltzmann kind of, I'm not sure if they worked together or not, or independently. So then they came up with this distribution to describe the molecular speeds of a gas, you see. So when Einstein came and invented general relativity, right, he used the form of mathematics that had already been invented by Riemann 100 years before him, Gauss and Riemann, the mathematics of multi-dimensional space. It had already been invented. So a lot of times that math that abstract mathematicians are working on, or maybe even applied mathematicians, maybe at this time they don't see a use for it, but in the future 50, 100 years, somebody else is gonna come along and use that, you see. So this distribution function then comes along to the gases. Back to the Maxwell-Boltzmann distribution, how does it work here? It looks something like this, m over 2 pi kt, like this. M over 2 pi kt. So this is just the fudge factor that you need. But you see the main concept of it is that x squared e to the minus x squared. You see? That's what it is, x squared e to the minus x squared distribution. For that one, for x squared e to the minus x squared, you don't really need to do, and we go back to Desmos, you don't really need to do the x minus 80 on top. You see, for normal distribution, I needed, because there was no x in the front, I needed to go x minus 80 in order to make that the mean, you see. But for x squared, you don't need it. Look at what happens. I can go change this to I can just make this x squared. See, right now you see how the 0 is here, the peak. But as soon as I put an x squared in the front, what happens? You see? What happened when I put an x squared? See, when I don't have the x squared, what happens? Watch this. Get rid of that. You see here, the peak is at the origin. If I put an x, then you have a peak there, it shifts the peak there, and then has another one there. That's the Rayleigh distribution. Now if I do x squared, I make it like this, you see? So at the top, I don't need an x minus sigma, right? Okay, so now, then let's look at the thing here, the formula sheet, and let's understand what this is then. So you'll be given this, 4 pi n, 4 pi big N, then you have m over 2 pi kt, to the 3 halves, b squared, e to the minus nb squared over 2 kt. Now immediately you should notice that since kinetic energy is 1/2 mv squared, 1/2 mv squared, this means the kinetic energy, this part, is units of what? Kinetic energy. Kt is units of what? What was the units of K? Right, remember PV is equal to nRT, which is nKT. So when you see KT, it's units of what? Joules. RT is units of joules per mole. The KT is units of joules per particle. You see, so this is joules per particle. This is kinetic energy per particle. So joules cancels. That means you can't have e to some power, something that has units. The units should always be canceling when you take the e or ln, right? So this one is the kinetic energy of a particle over the temperature, kT of the gas. This is also v squared, which is m. So it's kind of related to, you can kind of see a kinetic energy developing here, but then there's some extra stuff going on. What is the extra stuff for? Well, when you take the NV, okay, so then the graph says what? The graph looks like this, right? Except for this graph, the graph doesn't go from 0 to 100, like in the case of grades. It goes from 0 to the fastest possible velocity you could have for a particle, which is infinity, right? So NV versus V in meters per second. So this gives you the distribution of how fast particles in a gas box are moving depending on the temperature of that gas, right? So some particle might be going almost no velocity at all. So no particle will be going at 0. So you're gonna have at least some particle that goes slightly above 0, right? Then as you go faster, 50 meters per second, 100 meters per second, 150, 200, so on and so forth. Let's say 2,000 meters per second, right? So then you're gonna have more particles going faster. So it's naturally gonna peak at a certain velocity, right? Then it's gonna go down. But it's not symmetric. In other words, this side of it doesn't look like this. Why? Because since this is forced to be 0, it's a little bit offset. The normal distribution, the other one for the grades, looks more like this. Comes, goes like this. And that one is more symmetric, I believe. This side looks like this. This one, this side is higher up than that side, right? You see how this side doesn't look? This side doesn't look like this side, okay? So the first thing we have to do is to say the area under the integral, right? The integral of this, dv, the integral of this should give you what? The number of particles in the box. So we have to normalize the function, right? So what's the integral of b squared? Let me just integrate this portion. Integral b squared e to the minus mb squared over 2kt dv, 0 to infinity. Let me just integrate that part. X to the power 2 times e to the power minus mb
X
squared,
should be x squared.
or maybe mx squared divided by kt.
You need another set of parentheses.
Something like that, right?
That should be okay.
Yeah.
Yeah. So now,
What two? Oh, it's 2kt.
well, it's 2 kt, right? Because of the kinetic energy, yeah.
What's that?
Okay. If they've already normalized that function for us, it should all work out so that we get the answer that we desire. Right, so the answer we're getting is square root of pi k to the 3 halves. So the square root of pi k to the 3 halves, and then we have temperature T to the 3 halves. Over square root of 2m to the 3 halves. Then we multiply that with all this stuff in the front. And if they did it right, everything should cancel and you should be left with just n. Right? So k cancels, right? K to the 3 halves cancels with this. M to the 3 halves cancels. Okay, you have a pi and pi to the 3 halves, right? And then you have 2 to the 3 halves, right? Well, one of the pi's cancels with the pi to the 3 halves, making it pi to the half. Pi to the half cancels pi to the half. All right, and t to the 3 halves also cancels. And 2 to the 3 halves times 2 to the 1 half
to the second.
is going to be 2 to the 4 halves, which is 4, cancels with 4, you're left n. In other words, the equation is given to you in normalized, right? So the area under the graph is the number of particles. Okay, the next thing to do, besides normalizing it, is to say, what is the velocity? We call that V most probable, or VP or VMP. V probable, or most probable. Most probable. It's the same thing. In other words, if I pick a particle in that gas, that's the most number of particles that are traveling at that speed. Okay? How do we find that? Then it's a simple derivative, right? We take the derivative of this and we set it equal to 0 to find the critical point. So dNV dV. So instead of integrating it, we're taking derivative. So of course this all stuff is constants. So it's just 4 pi n m over 2 pi kt to the 3 halves. So then take the derivative of this guy. 2b times e to the minus mv squared over 2kt plus v squared times e to the minus mv squared over 2kt times the derivative of this guy, which is minus 2 comes down, so mv over 2, no, 2 comes down, cancels with the 2, and you're left with kt. Right? That's the derivative of that. Then you can factor out this guy. Set it equal to 0 to solve for the critical point. Factor out another v. 2 is equal to, 2 minus mv squared over kt is equal to 0. Okay? Then you're left with V is equal to V most probable is equal to 2kt over m square root, or you could say square root of 2RT over molar mass. That's that. Square root of 2kt over little m, or square root of 2RT over big M. Okay, so that's what they did here. The most probable speed, Vp, is the speed most likely to be possessed by any molecule of the same mass m in the system, and corresponds to the maximum value or mode of f of v. Well, that means that's the mathematical equivalent of what we call mode, right? It's the value that exists most number of times, right? In statistics, that's the mode. To find it, we calculate the derivative, set it equal to 0, then we get square root of 2kt over m, or 2RT over m. Okay? So it says for a diatomic nitrogen N2, the primary component of air at room temperature 300 Kelvin, this gives us 2RT over M, 422. The next thing to do is to find the average speed. So this one is what we would call mode. So when you take statistics, they give you this kind of a problem. Let's say 10 people took a test. One person got 22, another person got 35, 48, 60, 72, 76, they would say, what's the mode? The mode is the one that appears the most. So this one, right? So even if they weren't given to you in that order, what you do is you put them on the number line, and the one that repeats the most, I think that's the one, is the mode, right? So that's what this is the particle that has the speed that occurs the most often, right? So this is the number of particles that have that speed. In other words, this would be the 60, you see? Then to do the mean, you would do the atom and divide it by 10, just simple, that one. The mathematical equivalent of doing that is to integrate d times integral, how many have that speed? In other words, you literally would do 22 plus 35 plus 48 plus 2 times 60 plus 72 plus 76 plus 80 plus 86 plus 98 over n, right? Over 10. So notice what you're doing. When you're doing that, you're simply multiplying how many people got that grade by that grade. That's what this is. How many particles are going at that speed? You're multiplying them. You see? Well, in this case, there's only two. Only this one has two. The other ones are individually different. But in that case, there's a bunch of them that are going at a certain speed. So that's why you're literally integrating. And then after you're done, you're dividing it by the number of particles. So then in order to do that, we would have to find the integral of d cubed. We would have to put a cube here, right? And what do you get here when you put a cube? So I would have to go here, put x to the power 3. This calculator is gonna go, what are you trying to do? Oh, came out simple. 2k squared t squared over m. Okay, so when I did cube, it actually came out simpler than the square. So then it came out what? 2k squared t squared over m squared. When I go 0 to infinity, d cubed. But then I have to multiply it by this stuff. Then I have to divide it by what? N. Right? And then the n's cancel, and you're left with 4 pi m to the over 2 pi kt to the 3 halves 2k squared t squared over m squared. Yeah. You have 4 pi m to the, this is 4 halves, so you have m to the 1 half. This is 4 halves, here you have k to the 1 half, t to the 1 half, then you have m to the 1 half, so then you have 2 pi to the 3 halves, then you have 2. 2 cancel. 2 to the 3 halves. Oh no, this is 2 to the 3 halves. 2. Eight pi over, one of the 2's cancels, over 2 to the 1 half, and then, pi, this is gonna be pi to the 1 half.
4.
Then you're gonna have square root of kt over m.
It's 4 instead of 8.
Hmm?
4 numerator.
Oh, 4?
Yeah.
Why'd you divide by n?
Huh?
Why did you divide by n? in the
Oh,
first-
because, just like when you do the mean, you divide by the
Oh, yeah.
10. Yeah, you're dividing by n. Yep. Okay, so that one gives you this guy. 2 over square root of pi. Square root of 8 RT over pi m, which is this one on the formula sheet. So I'm defining here C is square root of RT over m, and then I'm saying V average, that's this guy. So this is V most probable. V average is slightly bigger. It comes out to be slightly bigger because it's square root of 8 over pi. So notice this is, if you take this, this is square root of 16, right? 16 to the 1/2. So since it was 4, so then what we could do is write this as 16 to the 1/2 and then bring everything to the same radical. 2 goes into 16 8 times over pi kt over m. And 8 over pi is a ratio bigger than 2, square root of 2. So this one was square root of 2. This one is square root of 8 over pi RT over m. Okay, so the meaning of that would be the mean so the mean speed is the expected value of the speed distribution, the expectation value. This kind of stuff you're also going to do when you go to quantum mechanics, right? They're going to give you the Schrodinger wave equation of a particle. They're going to say, what's the expectation value that you're going to find the electron in the middle of the box or at some point with a certain uncertainty, right? So same topics, so a lot of times repeat in physics from one to the other. Expectation value. What's the probability of finding it? So now it ends up that physically neither the V most probable or the V average, they don't have physical significance that much when it relates to temperature. What really matters, remember earlier we derived the equation of 1/2 mv squared average is 3/2 RT. So in a 3D universe, right? We do 3D. So then what really matters is V squared average is, let me put KT here, is 3 KT over M square root of 3 KT over M. So this is 2 KT over M, 8 over pi is slightly bigger than 2, and then 3 is slightly bigger than that. So it shifts it to the right a little bit more. So what really matters is the next one. The mean square speed is the second order raw moment of the speed distribution. It's a weird way to say it. The root mean square speed is the square root of the mean square speed, corresponding to the speed of a particle with median kinetic energy. Oh, so what really matters is not the particle that has the mean speed, but the particle that has the mean kinetic energy. Okay? So in other words, if a particle is moving at a certain speed, what really matters is, it doesn't matter what the speed is. Take the speed of this, square it. Take the speed of this, square it. Take all the speeds and square it. That gives you their kinetic energy. Now, average those kinetic energies, find the average kinetic energy, and now square root it. That gives you the root mean squared velocity. You can see. And that's physically the most important. So in our distribution, that gives you even a higher velocity than the V mean, right? So if I wanted to know the root mean squared grade, what would I do? If similar thing applied for grades, I would square this grade, I would square this grade, square this grade, square those, 72 squared, 76 squared, 80 squared, 86 squared, 98 squared. I would add them, divide by 10, Then after I'm done, I would square root it. Let's see. So that's what they're gonna do next. They're gonna take this, integrate 0 to infinity, and then they're gonna get this. And then they're gonna put the degrees of freedom of the gas. Okay, so now if we did that, let's see, can the calculator integrate? So I would have to integrate x to the power 4 here. X to the power 4, e to the minus mx squared. Computer should blow up right now. Oh, okay, so that equation. Then multiply that by all that junk. Then whatever answer you get, square root it. Right? Now, this is the amazing thing of statistical mechanics. If this answer, after you've squared that and square rooted it, if that answer gives you the same thing that we calculated just from simply the box calculation, that's what Boltzmann couldn't believe, that when he derived the velocity that regular thermodynamics was giving him from statistical determination, but nobody wanted to believe him, that's what made him commit suicide, right? So he put this into the Desmos of his, I don't know how he did that integral, x to the power of 4, right? Right, so then you will get what? 3 square root of pi k to the 5 halves. 3 square root of pi k to the 5 halves, t to the 5 halves over square root of 2. Okay, so that to me is the real lesson in history. When you do a statistical analysis like this, you normalize it, you find the root mean square velocity, and it gives you the same thing that regular thermal gives you. Then that proves the statistical approach that you're deriving. You see? So then you multiply that by all that stuff, 4 pi n times m to the 3 halves over 2 pi to the 3 halves, pi to the 3 halves, k to the 3 halves, t to the 3 halves. God, it's brutal. Brutal. Right, and then divided by n. Okay, so now the n's cancel. Oh God, anyone wants to do that, or let's just believe it?
Just call it a day.
Just call it a day.
Yeah.
4 pi.
6 over square root of 2.
Oh, the m to the 3 halves canceled.
Yeah.
Okay, there you go. K T.
Simplified t.
The pi.
Oh no. This should have been 5 halves actually.
Oh, sorry.
KT over m.
The pi is gone. Pi.
Pi?
Yeah, it's gone. Because there's
1 pi uniform.
Oh yeah, pi to the half. Pi to the 3 halves gone. Okay, not too bad. So this is gone. This is gone. Then you have 2 to the 4 halves,
is gone.
which is gone. Oh, okay. 3.
That's weird.
Oh yeah, that's it. Then this is equal to v squared average.
Yep.
Then you take the square root of this.
Doesn't make it better.
Now, suicide. All right? Yeah, it worked out. You see, because of this 3, everything else canceled. And then square root of 3. That's why the normal distribution, remember it was called what? The Rayleigh was for 2 degrees of freedom, but the x squared was for 3. And for 3 degrees of freedom, you needed that 3 to come out. Oh yeah. Yep. Okay, well, what kind of a question is there on this type of thing on the test? You're just gonna ask us to integrate all that like Boltzmann and then commit suicide afterwards?
What? Oh,
Well, maybe something like this, let's see. Test run review, what the heck? Oh, is it?
Test cancel.
just continue. No, it's not.
I still wanna start, so let's finish this and then we start, chapter 19. The syllabus says 19. So even if I have to squeeze in for 10 minutes, we gotta do it. 19 is where it's really heats up. We start the first law of thermal, and we do heat engines, isobaric processes, isovolumic, isothermal. So far it's just kind of like child's play, you know? Okay, so it's a test review. Okay, let's say something like this. Not with necessarily the same numbers, let's change it around a bit. A chamber is filled with 5 times 10 to the 6 helium atoms and warmed to a temperature of 320 Kelvin. So let's say, instead of giving you the number of atoms, maybe I give you the number of moles. Let's say the number of moles is 20 moles, and I give you the temperature, 450 Kelvin, and let's say it's carbon dioxide gas. What is the translational kinetic energy per mole of the gas? So I'm asking kinetic energy per mole of gas. What is the root mean square velocity, the average velocity, and the most probable velocity? So V average, V most probable, and V root mean square. What is the maximum NV value? Actually, this problem probably will take us to the end. It's not that quick. So NV, it's asking us what's NV max. Okay, and then the last, what is the probability of finding a helium atom that is moving between, what is probability what is probability of finding the carbon dioxide going at 800 meters per second? Okay, so if you have the number of moles, you can calculate the particles easily, right? So Avogadro's number times the number of moles, 6.022 times 10 to the 23rd times 20. So each mole has that many particles. So then that's gonna be 12.044 times 10 to the 24 particles. Okay, kinetic energy per mole of the gas. So the kinetic energy per particle is gonna be 1/2 mv squared. Then you multiply that by, this is per particle. My stuff. Let's see. Which is equal to, you know what we could do is energy per. Or we could also do this one, V average, V most probable first. V most probable is square root of 2RT over big M. V average is square root of 8RT over pi M, right? And then V root mean square is square root of 3RT over M. Right, remember the ones that we got, 2, 8, 3. So then this is 8 over pi. So then we have here 2, 8.314, 450 Kelvin. And then carbon dioxide's molar mass.
28.
Carbon is 12.
32 and 12. 44.
44, yeah. 0.044. So the idea behind that is that if a gas is a certain temperature, but if it's heavy, it doesn't have to go as fast. You see? Doesn't have to go as fast in order to be that temperature. If it's a light gas has to travel faster to be at the same temperature as a heavy gas. You see? That's why the Earth's atmosphere doesn't have a lot of hydrogen and helium, the light elements, because those elements go faster than carbon dioxide and oxygen, right? So because they go faster, they escaped our atmosphere a long time ago. Our gravitational pull of the Earth is not too strong to keep hydrogen and helium, you see? But Jupiter has a lot of hydrogen and helium because its gravity is a lot stronger. So in its atmosphere, it's got 90% hydrogen. The sun has 90% hydrogen too, right? Because its gravity is so strong, it could keep those molecules even though they're traveling very fast. Earth only has primarily nitrogen, the heavier elements, a little bit carbon dioxide, nitrogen, oxygen. Well, those molecules are not moving as fast because their molar mass is higher, you see? Okay, so. .38 meters per second. Now this one is gonna be slightly bigger. It's the mean. This is the mode. This is the mean, right? So then you do now divide this by 2 to the square root equals times 8. Slightly bigger, I'm getting 465. Right, meters per second. Remember, graphically, it looks like this. Like that. V most probable, V average, slightly bigger, V root mean square, slightly bigger. It kind of makes sense, graphically, it kind of makes sense to me why this is also more important. Because if you take this, you're ignoring, remember how I said the graph is not very symmetric? It's more like this. It's not like the normal distribution. So if you take this as the most important, you would almost ignore the particles that are moving faster. You see? Their velocities would not count. So V root mean square is actually more meaningful because it takes into account particles that are traveling a lot faster. Does that make sense? So those guys contribute to the temperature of the gas too. Because it's not symmetric, you can't just go here and say, oh, this is the middle of the whole thing, and therefore this is the most important. You gotta go a little bit more to the right. You see? With a normal distribution, the average is the average, because on this side and on this side it's the same. You see? So now you go divided by square root times okay, 505. Okay, so therefore the kinetic energy per particle is going to be 1/2 m. And then if I say this is the 1/2 of, why am I stuck? Per mole. Molar mass. Oh, okay, yeah, okay, so then instead of doing 1/2 mv squared, I'm gonna do, because I wanna know the kinetic energy per mole, I should be doing the molar mass. Right? Yeah, exactly. 1/2 m big mv squared. Right? So then I would do what? 0.044 times 505. 0.06 squared. Or the other way to say it would be what? Since V squared is 3RT over M, you could literally do what? Square this, 3RT over M. The other way to do it would be 1/2 mv squared, and then say 1/2 m, V squared is 3RT over M. M cancel, 3RT over 2. Right? That would be the direct way of getting the kinetic energy per mole. And it'll give you the same as this. So 8.314, 450 over 2. (5,611.95 joules). Or you could do easily like 5.61 kilojoule kinetic energy per mole. Okay, nice. Next one. Okay, we got this. So what is this one asking? NV max. It wants to know how many particles are moving at the most probable. You see? So how many particles is that peak? Remember, the area under the graph is the total number of particles that we have is 10 to the 24th particles. But if I want to know what that peak is, how do I get it? Well, look at this equation. Back to the formula sheet. back to the formula sheet. Oh, by the way, I never talked about this equation. How did this equation come about? It's a simpler form of this. After we derived the most probable, VP, what was VP? Square root of 2kt over m, right? You can take this and put it back into the you could take that and put it back into here. So you see m over 2kt over m. This one can come down there. That'll be VP squared. You see that? So it's a easier form of writing this equation. So VP squared. And then here 2kt over m, also VP squared. Right? So then this becomes VP squared. And then you already have a V squared. 2kt over m becomes VP squared, V squared, and then you have an extra VP because this is 3/2. So you kind of basically rewrite this in terms of the V most probable. So now if I want to know how many particles are moving at V most probable, put V is equal to VP. So that gives you that maximum value. So e to the minus 1. Right, so how many particles are going there? So we have NV is equal to what? 4N over square root of pi VP times what? V over VP, quantity squared, e to the minus V over VP squared. So if I want to know how many particles are going at that, you just put here 1, put here 1, and that's it. The only thing is this, put the number of particles over VP. So the number of particles is what? 12.044 times 10 to the 24th over square root of pi. VP is 412.38 e to the minus 1, and then this is already 1. See?
2.4247
2.42,
47 10 to the 22.
yeah,
It's a lot.
particles.
A lot of particles.
And that's the most, right? Going at that velocity. What's gonna happen as I increase the temperature of this gas? Let's say I quadruple the temperature times 4, and then the temperature becomes 1,800 Kelvin. What should happen to this distribution of gases?
Shift.
Exactly. It's gonna shift to the right, but the other thing that's gonna happen, okay, if I quadruple the temperature, what happens to the V most probable?
It double.
Double. What happens to the V average?
Double.
Double, double. So everything shifts twice. So it kind of looks like this. This goes V most probable, V average, V root mean square. What happens to the MV?
Nothing.
This is 1, this is still 1,
Nothing.
but this one doubled.
Oh, right.
So literally the graph goes, shifts over and then goes exactly half of this. So it looks like this. See? So a star that is 4 times hot as the sun, right, has more particles that are traveling faster, and the distribution of speeds is shifted more to the right. That's why that star is hotter. More particles in that star are moving faster, and they're moving on average 4 times faster. And that's why that star is twice as hot as the sun. And then if you look at the Stefan-Boltzmann law, if it's 4 times as hot, it's gonna radiate, ooh, that's a lot. 16 times 16, 256?
280. Yeah.
256 times as bright. Remember the other graph that I told you about? The luminosity? And I said it shifts to the right, shifts to the right, and I said we're focusing on the area under that graph. That's not really related to this, but it does have the same kind of behavior. This one tells you the wavelength of the light that's emitted and the intensity of radiation. The area under that graph is the power radiated, the total power radiated. So what happens to the area of that graph as a star gets hotter? It shifts to the left, and the area gets 16 times more. So for this one, as you get cooler, the wavelength gets further to the right. You start radiating in the red. As you get hotter, you radiate this way, and then you go up. For this one, opposite happens. The molecular speed, as you go hotter, it shifts to the right, and it gets wider. And the peak goes down. Because what happens to that star is that more molecules are moving faster, so less molecules are moving at the V most probable. Half of them, right? Interesting how that all works. The distribution shifts, goes down in half, and everything doubles. So if this doubles, NV gets half. Okay, so then the last kind of question is what is the probability of finding a carbon dioxide molecule? So that one is a kind of an area question. So if I want to know something going at 800 meters per second, basically I want to know the area under this graph divided by the total area. So what's the chance of finding a random particle going at 800 meters per second, but with an uncertainty of 20? So what's the uncertainty? So if it's going at 800 plus or minus 20. So that means I want to find the area of a rectangle with 20 this way and 20 that way. So the base is 40, right? So the base of this is 40. So then what's the area going to be? So for part D, area is going to be NV times delta V. So I'm going to take this NV that I have, 4 times 12.044 times 10 to the 24 over square root of pi for 12.38. So that's this stuff. But here I'm going to put 800 for my V. 800 over VP. What was my VP? 412, right? 412.38 squared e to the minus 800 over 412.38 squared, and then divide that by the total area, which is the number of particles. So you're getting this guy, which is the peak, right? The NV. Then you multiply that by the thickness of that rectangle, NV times the thickness, then divided by the whole area, which is the total particles. So the total particles cancels the total particles, and then you just have left this guy, okay? mole. Oh, I made a mistake. It's hard to do it on the phone.
I got 4.7789, 10 to the negative 4.
And then you multiplied it by 100?
No. I forgot.
4.7799 times
89.
100%. So convert it to a percentage. Area over n
Wait, what?
times 100%.
You have to convert it to percent.
Because it says, what is the probability of finding the...
But we didn't multiply by the delta V, right?
Oh, yeah. Then multiply it by delta V, which is 40.
I just realized. 40.
Times 100.
40 times 100. 1.91.
Okay. Nice. That's chapter 17 and 18. Okay, so we'll start 19 on Wednesday then.